context of directed spaces.
Thank you for the presentation, and thank you for giving me the opportunity to present my work here. So I will talk about directed algebraic topology in this talk, and mainly my line of work is to construct analog of classical construction from algebraic topology. And so here I will mainly focus on homology. Well, I'm sorry, because there will be a non-empty intersection with the previous talk, so maybe I should skip some true concurrency. And what you have to remember is that this. We model concurrent systems geometrically with some directed spaces, and execution will be modeled by directed paths in those topological spaces. And we can also model equivalence of execution modulo scheduling of independent actions with an analog of homotopy in this directed setting. So I will also consider these spaces, so I will not take too much time on this. Maybe what you have to remember is that the set of die paths may be equipped with a topology coming from the compact open topology from the space of paths. And also the set of die paths between 2 points may be equipped with a subtopology. And those objects will be called die path space in the following. Okay. The axioms of a D-space are very simple, which permits to add some directed structure on topological space quite easily. For example, there is at least 3 interesting structures on the segment. The first one, that I will call the directed segment, is a structure where the die paths are all the monotonic paths. But there is also 2 other structures that are actually more general from a topological space. There is always 2 ways to add a directed structure on a topological space, namely the lowest one, where the die paths are the constant paths, and the largest one, where the die paths are all the paths. They all have their own interest, but for example, the directed segment has the following property, that the die paths in a D-space are actually the die maps from the directed segment to the D-space. So, as I told you earlier, we can model equivalence of execution using an analog of homotopy in this directed setting. So, classically, a homotopy is just a function from this project of segment into space with some boundary condition, but equivalently, a homotopy is just a path in a space of paths. And 2 paths are homotopic if they are in the same path connected components of in this space. So we can do exactly the same in a directed setting. We just have to choose which structure to add on those segments. So we choose the following ones. That is, here we choose the die paths as the constant paths, and here the die paths are monotonic paths, which means essentially that a dihomotopy is a continuous deformation of die paths, during which we stay a die path during the deformation, but we do not care about the directedness of the deformation itself. Equivalently, this says that a dihomotopy is just a path in the space of die paths. But we could have chosen other structures. For example, some authors choose to put here the directed segments too, which means equivalently that we have a dihomotopy is a die path in a suitable D-space of die paths. Well, if you know a bit about higher categories, considering dihomotopies like as paths in a space of die paths, this means that you consider D-spaces as some kind of infinity 1 categories, while considering dihomotopies as some die paths in some D-space, it's considering D-spaces as infinity categories. Somehow. I can make more precise this statement, but I will not do it here. Okay. So let me show you an easy example. here we have a simple D-space where, so it's just a square in which we are carved a smaller square. And the die paths are component-wise monotonic paths. So we have depicted two die paths here, which are dihomotopic because we can continuously deform one to the other while staying in die paths during the deformation. On the contrary, those two die paths here are not dihomotopic because will be blocked by the hole in the middle. But as Lisbeth says in this talk, we do not see why it is important to stay a die path during the deformation. Namely, dihomotopy and homotopy coincide in such spaces. But actually, things can go wrong in these spaces. So it's a different example than the one from Lisbeth. But I think it is even worse because it's, I will call it the matchbox. It's just a cube, a hollow cube, in which we have cut the lower face. And the die paths are paths that can only go from bottom to top and from ground to background. And so we have two particular die paths, here in blue and here in green, which are homotopic, because we can continuously deform one to the other just by going around the cube. But as you can see, in this deformation, we can go through some paths here that must go from top to bottom, and so which is not a die path. So this homotopy is not a dihomotopy. Actually, there is no dihomotopy between those two die paths, which means that they are not dihomotopic. But as you can see, classically, this space is contractible. So any classical construction from algebraic topology will give you nothing on this space. While, as I showed you, there is something non-trivial in the dihomotopy type of this space. So it will be hard to use only classical construction to detect something on a dihomotopy type of this space. Okay. So for my line of work, I would be interested if there were some categories whose morphisms are die paths. That is this a category? The answer is no, because concatenation is not associative. But we can solve this problem by just quotienting everything modulo dihomotopy, which make this into a category, and this is actually what we call the fundamental category of a D-space. But we can do a bit better, because in fact, concatenation is associative modulo non-decreasing surjective reparametrization. So instead of quotienting everything by dihomotopy, we can quotient up to those reparametrization, which gives the notion of a trace in a D-space. That is, a trace of a die path is just the equivalent class of such die paths up to such reparametrization. And we can form what I call the category of traces, whose morphisms are actually those equivalent classes that are called traces. And much as the space of die paths, we can put some topology on the set of traces just by quotienting the topology of the space of die paths. And I will call those objects a trace space. Okay, I've presented you all the basic notions that I need for my talk. And the goal here will be to use all those basic constructions to study these spaces and construct analog of classical construction from algebraic topology. And mainly, I will focus on homology here. So let's go. There were many candidates of homology for these spaces, which were proposed. But, well, they are not precise enough to detect something on a space like the matchbox. Typically, some of them are constructed by just considering classical homology of the space and adding some structure on this space. But the matchbox being contractible, its homology will be trivial. And so adding some structure on something which is trivial will only gives you something trivial. So we will not be able to detect something doing this. So we must be a bit more clever to detect default of Dihomotopy in the matchbox. So the basic idea is we will look at trace space or pi space, which is somehow equivalent for the space I will consider. And the thing is very similar to concurrent systems. In concurrent system, what you look at is just you look at executions. And for example, if you consider geometric realization of concurrent system, such as those spaces, we can say, okay, just look at the trace space between the endpoints, which somehow will give you the maximal execution of your system. And say, okay, homology of such this space will be just the homology of the trace space between those points. The problem is that in concurrency, we know that considering only maximal execution is not precise enough to distinguish systems. What we do in concurrency is looking at all the possible executions, even the partial one, and look at how they evolve with time. And we do exactly the same here. Because if you look at the trace space between the endpoints here, those trace spaces are equivalent to a 6-point space, so you will not be able to distinguish this space using this. But if you look at all the possible trace space between all pair of points, you will be able to distinguish those two, because if you look at the trace space between those 2 points, you have a space which is equivalent to a 4-point space. And you can check that in this space, there is no pair of points between which the trace space has this homotopy type. So that's the basic idea. We will look at, essentially, all the trace space between all pair of points, taking their homology, and look at they evolve with time. So I must be more precise by what I mean by how they evolve with time. And I will do it like this. I will consider homology as a functor from some indexing category to a category of module. The indexing category will be the following category, whose objects are traces and whose morphisms are what I call extensions. That is, pair of traces that extend some traces in the middle. And I will define homology as a functor from this category to the category of module, which will map every trace to the homology of the trace space between its endpoints. So there is 3 remarks that we can make on this slide. First, I call it natural homology, this homology, because this category is called the category of factorization of the trace category that I presented you earlier. And a functor from a category of factorization to a category of module is called a natural system in the literature. The second remark is that we have a shift in the index here. I will explain it in the next slide. And the third remark is that I use as index the traces, while I use only pair of points to compute homology. Well, the thing is that we can define exactly the same way a natural homotopy, but this time we need the trace to point the space in order to take its homotopy group. Now I can explain why there is a shift in the index. Well, the thing is that I would like the pi1 to be related to the fundamental category somehow. And it's the case when you take pi0 here. So for the third remark, we can actually do a bit better because we only need a pair of points to index to compute homology. So we can consider, instead of the category of factorization, we can consider the enveloping category whose objects are pair of points which are accessible one from the other, and define homology exactly the same way. And I will call it bimodule homology because, well, a functor from an enveloping category to a category of module is called a bimodule in the literature. Okay, so I have two theories a priori of homology, the bimodal homology and the natural homology, but I will show you a bit later that they are somehow equivalent. So it's not important. So let me show you an example. Let us consider the two copies of the directed segment whose endpoints are glued. The category of factorization of the trace category has this form. All those are traces which correspond to subsegment of the upper segment. Traces here are subsegment of the lower segments, and we have two top elements which correspond to the two segments. And the first natural homology will map all those to the homology of the trace space between points which are not both endpoints. And so since this trace space is contractible, we will have many copies of the ring. And there is just the two top elements which correspond to traces which go from 0 to 1, for which the trace space is homotopically equivalent to 2-point space. So we'll have two copies of R2 at the top. The bimodal homology is pretty similar. The only thing is that the two top traces have the same endpoints, so we just glue together the two top elements. Another example is the matchbox. As I told you, between A and B here, there are two dipaths that are not dihomotopic. From a topological point of view, we can prove that the trace space between A and B is actually homotopically equivalent to a 2-point space. So in the first natural homology of the matchbox, we would have a copy of R2 somewhere, which means that the first natural homology is not trivial. You will have something non-trivial on the first natural homology. So you will be able to detect failure of dihomotopy in this first natural homology. Okay, so now that I have those structures, which are essentially huge collection of modules and morphisms of modules, how do we compare such structures? Because the interest of homology is that you have spaces, you compute their homology, and you somehow want to know if those two spaces are equivalent, so you have to compare homology typically by isomorphism. So is there a notion of isomorphism for such structures? The answer is yes, because bimodal homology and natural homology are both instances of what is called diagram in category. That is just a functor from a small category to a category of to a specified category, typically a category of module. And there is a notion of morphism of diagrams, which is just pair phi sigma, where phi is a functor between the domain of the two diagrams, and sigma is a natural transformation from F to G phi. And an isomorphism in this category is just such a pair where phi is an isofunctor and sigma is natural isomorphism. And we can prove that all our constructions are actually functorial for this category. So the question is, can we compare our diagrams of homology using this notion of isomorphism? The answer is not really, because our homologies are defined using the trace category, which keeps essentially all the information of the D space. And so comparing homology using isomorphism or diagram will not give you more than isomorphism of D space. So it's not really interesting things to do. Remember that we have in mind concurrent systems. And I told you that we want to somehow compare things like, okay, trace spaces correspond to somehow executions in your systems, and we want to look at how they evolve with time. So we do not care the fact that they have precisely the same traces. What we want is that they have the same evolution of traces. And so it's natural to consider bisimulations to compare our constructions, because that's exactly what bisimulations do in concurrency theory. They only look at how things evolve with time. And for example, it would be interesting that this, which is the first natural homology of the example I gave you earlier, it would be interesting if it is somehow equivalent to such a diagram, which is just some copy of R which are interleaved, and on top you have two copies of R2. So there is a general theory of bisimulation, which I will not explain here, and we can make precise the intuition from concurrency theory in our setting. But it requires a bit of work, and I think the simplest way to define bisimulation here is the following definition. We will consider particular morphism of diagrams which will have very strong property that will assure that they have the same evolution with time. Those morphisms will be called open, and there are also pair of such things where the natural transformation part is actually an isomorphism, but this time the functorial part is only surjective on object and vibrational, meaning that it lifts morphism. And we say that two diagrams are bisimilar if there is a zigzag of such morphism between them. Actually, we can prove that only a span is needed. Okay, so now we have our structures, we have the way to compare them. So let me show you some examples. So, as I told you, the first natural homology of the gluing of two directed segments will be equivalent to these finite diagrams. Actually, there is an open morphism from this one to this one, which is depicted with the color. Maybe it's not very well. What we can prove also is that there is an open morphism from natural homology to bimodule homology. So both notions of homology are equivalent for this notion. And what we can prove also is that the first natural homology of the matchbox is actually not bisimilar to the natural homology of a point, which means that bisimulation do not lose information, typically default of Dihomotopy. Okay, so now we can prove some properties on this homology theory. The first one will be computability. So what we want to do is we have some D spaces. We have their homology, which are not really finite because we must index by traces of our pair of points, so they are not really finite. But we would like somehow to compute finite diagrams, such as this example, which will be equivalent to homology, and then compare those finite diagrams, which will allow us to decide if two D spaces, at least nice D spaces, have the same homology. And we can do it for Euclidean cubical complexes, which are essentially finite union of cubes in a Euclidean space. In such a space, we can describe what I call discrete traces, that is, traces that only join a center of consecutive cubes, such as this red one. In a Euclidean cubical complex, there is a finitely many such traces, and so we can describe all of them. And we can actually restrict natural homology, at least its indexing category, to such traces, which gives you a finite diagram which is defined exactly the same way as natural homology, except that you consider only those discrete traces. And the point is that we can explicitly compute this diagram. That is, we have finitely many such traces, we can all describe them. And then for all traces, we can compute a finite representation of the trace space between its endpoints, typically using the representation that Martin gave last week. Or maybe I think the talk of Christoph will present another one, maybe. And from this finite representation, we can compute homology. So we can explicitly compute it. Then we can decide the following problem. Given two Euclidean complex, do we know if they have the same homology, at least when homology is computed in reals? The thing is, we just compute those finite diagrams, and then we can decide by similarity, at least in reals, which can be reduced to the existential theory of the reals, which means essentially that knowing if a polynomial equation has a solution in reals is decidable. Okay, the next property is exactness. In classical algebraic topology, exactness as the original form of the exactness is the following. It states that there is a long exact sequence in homology that relates relative homology with homology of spaces. Actually, there is a more general form which says that every time you have a short exact sequence in chain complexes, then you have a long exact sequence in homology. Actually, this theorem is purely algebraic. As long as you have a homology theory, which comes from homology of a chain complex, typically singular homology, simplicial homology, and as long as it is with value in an abelian category, typically in modules, then you have such a theorem. Well, the problem is that the category of diagram is not abelian. There is no zero object, for example. So the question is, do we have ingredients that allow us to prove such a theorem? Well, the ingredients needed are at least that we must be able to talk about a chain complex. So we must be able to say that a morphism is a zero morphism. In abelian category, it is done with zero object, but we can do it also in diagrams because we have diagrams which is with value in trivial modules. So we can call a null morphism a morphism whose natural transformation part is just a collection of zero morphism. Then to talk about exactness, we must have some kernels and co-kernels. In modules, kernels are defined as some equalizer. And actually, in diagrams, we do have equalizer. And essentially, a kernel in diagram is just a diagram of kernels. So they are very simple to compute. Co-kernels in modules are computed as some co-equalizers. In diagrams, we do have a co-equalizer, but they are much more complicated. But we do have them. And then, to say that homology theory comes from a homology of a chain complex, we must be able to say that we have subquotients, because homology is defined as the quotient of a kernel by an image, which are both submodules of some modules. So more generally, in category, we must be able to say that we have the quotient of a subobject by another subobject, which is a bit technical, but we do have this in diagrams. Essentially, all those ingredients say that the category of diagram is homological. And in a homological category, we almost have an exactness axiom from 3. Well, modulo the work of Marco Grandis. So there is a theorem which says that in a homological category, every time you have a short exact sequence of chain complexes, you have a long sequence in homology, but it is not exact everywhere in general. It is only of order 2 everywhere. That is, the composition of two following morphisms are null, but not exact in general. So we do have a theory of exactness in diagrams, but it is not as nice as in modules. Okay. Lastly, I would like to talk about the homotopy axiom. In classical algebraic topology, the original form of the homotopy axiom is the following. It states that if two continuous functions are homotopic, then they induce the same morphism on homology. This has the following easy consequence that I call the first version of the homotopy axiom, that an homotopy equivalence induces an isomorphism on homology. This statement can be made more precise because actually a weak homotopy equivalence, that is a continuous function that induces isomorphism on homotopy groups, also induces isomorphism on homology. So the question is, do we have some dihomotopy axioms for our homology theory? Well, we do have a second version for free, because if a dimap induces isomorphism of diagrams between natural homotopy, then it also induces an isomorphism diagram between natural homology. It's free because it's just applying homotopy axiom on trace spaces. But as I told you, comparing things up to isomorphism is not a good idea. So do we have something better using bisimulation? The answer is yes, and it's almost as free. It is stated as follows. If a dimap induces an open map between natural homotopy, then it also induces open maps between natural homology and bimodule homology. And it's free because it's also just applying homotopy axiom on trace spaces. And then it's just reasoning on open morphism, which is purely categorical. We do not have geometry anymore. It's just category. Now, do we have a first version of a dihomotopy axiom? Well, the answer is yes, but it depends on what you mean by dihomotopy equivalence. And there is no real consensus by what we mean by dihomotopy equivalence. So I have a notion of dihomotopy equivalence which allows to have a dihomotopy axiom, but, well, it is defined as follows. It is defined using some deformation retracts in a directed setting. So a deformation retract classically is just homotopy, that is a function from a space to a space of paths. But in a directed setting, we couldn't use die-paths because they have a very bad property. That is, well, classically, the continuous function, which is induced by concatenating some paths to other paths, is a homotopy equivalence because a path is always invertible up to homotopy. In directed algebraic topology, it's not the case. Such a continuous function where you replace a path by a die path and the space of path by a space of die path, this is essentially never a homotopy equivalence. And if you define a notion of dihomotopy equivalence using die paths, what you will get is a notion of equivalence that do not even preserve the homotopy type of a space of die paths, which is pretty bad. So we have to do a bit better, and instead of using a space of die paths, we use a space of paths that do induce homotopy equivalence by concatenation, which I call inessential die paths. So it's the largest class of die paths that induces homotopy equivalence by concatenation, plus some more axioms that I can justify, but well, whatever. And I can justify my notion of dihomotopy equivalence, well, mainly, well, as I told you, where it is. The fact that we use die-paths that induces homotopy equivalence is a nice thing, because we said that such an equivalence will preserve the homotopy type of the die-path. And this property means that this notion of dihomotopy equivalence has actually a deep relation to equivalence of infinity one category. I can't make precise this, but it's a bit technical. Another good property is that the action of such equivalence in the fundamental category is that we compare fundamental category by comparing the category of components. For example, if you look at classical dihomotopy equivalence coming from Marco Gandi's work, what you get on the fundamental category, it's groupoidification. And it is known that groupoidification loses many information on the category. For example, all non-constellative behaviors are lost with groupoidification. And so we do have, with this notion of dihomotopy equivalence, a dihomotopy axiom, at least for, well, Euclidean cubical complex, but for more general spaces, but whatever. So it states that if two Euclidean cubical complexes are dihomotopy equivalent in my sense, then their homology are bisimilar, which means that, okay, maybe my homology series are not invariant by dihomotopy equivalence in general, but it is at least for spaces on which we can do computations. So it's not that bad. And I think it's everything I have to say. So thank you for your attention.
Questions, comments?
Yeah.
Yes.
You had a theorem that bisimilarity for homology with coefficients in R is understandable or computable, and it was based on the computability for the reals. So there are 2 points. One is, where do polynomials enter in this at all?
Oh.
And the other question is that for the theory of the reals, that in principle, is a very, very complicated elimination of quantifiers, which will have big towers of exponentials.
Yeah.
And do those really arise in bisimilarity questions?
Yeah. So the main point, okay, where is the definition? Yeah. There is an equivalent definition of this, which is more related to computer science, where two diagrams are bisimilar if there is a relation between the states of the domain, and more than a relation, we do have an isomorphism between the image of those objects. And it is precisely the fact that you must have an isomorphism which can be encoded by polynomials. Because, okay, everything can be encoded by linear equations, but the fact that you have an isomorphism can be only coded using, well, polynomial of degree 2. And that's where you use polynomials. And it's true that it's a hard problem to know if a polynomial has a solution. I think, well, the full problem is in X space, but if you consider only existential, so just if there is a solution of a polynomial, it's in P space. It's much simpler than just a tower of exponential.
Any other questions?
So if I understand it correctly, kind of your construction of natural homology essentially goes in 2 steps. You first approach a category of trace spaces to the space, where you have essentially category enriched in the homotopy category of spaces, and and then you pass to homology.
Mm-hmm.
And this can be noted of inessential equivalence related that it induces an equivalence of categories enriched in the homotopy category of spaces.
Well, I don't know. Can you repeat the last part of your question?
So, if I understand it correctly, so if you have kind of a map between directed spaces, you get kind of a morphism of categories in which in particular category of spaces or traces.
Mhm.
So, I mean, there you have kind of notion of equivalence of such things. So, you get the notion of that something's an innocent equivalence of directed spaces. So, how's the relation to being kind of inducing an equivalence of the associated categories in which in one?
Okay. So you have a category enriched in topological spaces, right, with the trace category. Actually, if you apply the singular singular complex functor on this category, you get a category enriched in simplicial sets, and this gives you actually an infinity one category. So that's essentially what I mean, but there is a deep relation with inessential equivalences. But actually, inessential equivalents do not induce an equivalence of infinity one category on those things. Mainly because, well, in the equivalences, you look at, well, there is two conditions, but the first condition is to look at the one skeleton of this category, which gives you the fundamental category of the space, essentially. And my point was that inessential equivalents do not induce equivalence of categories between fundamental categories. So, well, you can prove that you have almost an equivalence of infinity one categories, but not exactly. You have to be a bit more clever. But yes, they are related.
We have a lot of time, please.
You mentioned infinity one categories, but when you consider bimodules, sometimes it's more natural even to one step further up to consider infinity two categories.
Huh.
That would be natural. Have you thought about the naturality of that?
No, not really. Well, I was interested in, well, mainly to have some kind of Dihomotopy hypothesis. And in my mind, these spaces should be somehow infinite one categories. So no, I didn't look at infinite two categories. But yeah, that may be a good idea.
But one further thing, when you look at these directed categories, and if you take the nerve of those categories, you then capture the homotopy type or the directed homotopy type by the nerve construction.
Well, I don't know actually.
Okay.
But that's yeah, I think so.
It's interesting, they're dealing with the topological categories where all the objects are also topological space. So makes it slightly more complicated. Another question? Well, let's say.
So the reason I like, exact sequences in homology, like singular homology, whatever, is because I can use it to calculate, like USL or something. Can you use these exact sequences? So, you add some maybe blocks or abstraction to calculate. Like, what's the purpose of having this exact sequence except just for that?
Yeah. Well, I think exact sequences can only be used level-wise. That is, well.
I mean, like, I would like to say, so, do you have like a notion of like maybe building up, like maybe cell decomposition?
No.
And like, and that's how my homology will change when I do this operation?
No, I don't think. No.
You have something like that on the individual trace spaces, but no.
Yeah. The problem of the trace space is that it is not very modular, because, for example, it is not compatible with union, and which makes things a bit complicated.
Some other, I'm saying like, maybe there's some other way of like, okay, this is an operation. And this is I can control change of the homology.
Yeah, that would be interesting, but I think we do not have this for the moment.
Yeah, so I guess my question was along the same lines as Vortex, that your calculations are using these discrete trace spaces, but as you double the size of this directed space, these trace spaces are going to increase a lot. So it would be nice if you could do like a partial computation and then extend it somehow.
Yeah.
Some sort of calculator or something.
Yeah, I think we can do a bit better. Well, I index everything with those discrete traces, but we can do better, I think. Well, my point was to have something finite, but well, I think we can do better by considering more clever traces. But I think that well, we have the same problem if we double the, well, essentially if we do a subdivision, we will have essentially much more traces. But maybe we can do a step of simplification before doing all the computations. That is, well, we have many traces, but then we may check if two traces which one extend the other are essentially the same, so we can just skip one and decrease the number of traces to consider. I think we can do this.
We can't really blame the subject for that, because, I mean, this is a very nonlinear theory, right? Because when you concatenate, say, two cubes by putting an endpoint to an endpoint, there's sort of a tensoring going on, rather than just an addition. So, you know, so slavishly following usual homology. It's maybe a mistake to call it by the same name, because it causes people to want to do that, but the problem you shouldn't.
Yeah.
Any other remark, question? Please.
The zero diagram, why is it not a zero object? Why does it appear to be a zero object?
Sorry?
The zero, you mentioned the zero diagram, or the diagram is null diagram. Why is it not a zero object?
Well, because well, a zero object is an object which is both initial and final. And in diagram, the initial object is an empty diagram, and the final object is the diagram is just one point, which is mapped to the trivial module, essentially.
Thanks.
If there are no other questions, let's